want to design a basic gate called inverter. So an inverter is a NOT gate. An inverter is a NOT gate. So as you know, NOT gate is nothing but inversion of input. The gate itself gives inversion of input. Now coming to gates, we have to deal with logic levels. Till now we have discussed MOSFET operation where we have just dealt with voltages. So N-channel MOSFET carriers are electrons, but gate to source voltage, drain to source voltage is positive. P-channel MOSFET, gate to source voltage, drain to source voltage is negative. So whatever it may be, in terms of logic levels, logic 1 means 5 volts. Logic 0 means ground, 0 volts. Okay. So depending upon the requirement NMOS and PMOS, corresponding voltages are applied. But when you go to logic gate, it deals with logic levels. So in an inverter NOT gate consists of inversion of input. Logic 0 at the input gives logic 1 at the output. Logic 1 at the input gives logic 0 at the output. So for this, we have to design the inverter with MOSFETs. So if you consider your MOSFET NMOS, it is good in transmission of 0. It is poor in transmission of 1. So what is an inverter? An inverter requires two output levels. An output of logic 1 should be got when your input is 0. And an output of logic 0, you have to get it when input is 1. So either way, you require output as 1 and 0. So for which you need to connect your MOSFET to VDD and as well as ground. So if you select, there is a logic called pull up and pull down. Pull up means because if you want output to be logic 1, you have to connect pull up to VDD. Pull up is one logic where we connect output to VDD. Pull down is another logic where we connect output to ground. So if you select pull up as NMOS, what happens? If pull up is NMOS, NMOS are bad in transmission of logic 1. So there is a drop of minus threshold voltage. So VDD will get output as VDD minus VTH. That's why always pull down is selected as NMOS. Pull up is any other logic. Okay. So continue with pass transistor. You listen. Today class we are going to cover NMOS inverter, a NOT gate designed with NMOS, a NOT gate designed with CMOS consisting of PMOS and NMOS, a NOT gate designed with BICMOS, CMOS with BJT. And we'll discuss these topics in coming classes.
The name itself, it is saying that passing the logic through transistors. So if you arrange transistors in series like this, then each transistor can pass the logic from one node to other node up to output. If any one of the transistors off, then this input logic will not be passing to the output. So MOSFETs can also be used as switches in series with lines carrying logic levels, as in the case of relay contacts. Such kind of logic is known as pass transistor logic. Pass transistors pass the signal between the drain and source terminals. So this is a pass transistor logic arrangement by using NMOS transistors. If VGS is equals to 0, then the transistor is on. So VGS is nothing but this is the gate terminal, this is the gate, this is the gate terminal. If VGS is equals to 0, then the transistor becomes into off, hence no connection between the input and output. Then output will goes to 0. If all the transistors become on, then output X is equals to A and B and C. So this one, X is equals to A and B and C. NMOS inverter. So inverter is the basic element in the design of digital circuits. Without inverter circuit, it is not possible to design any logic circuit. So this is a symbol of inverter and this is a truth table. So if input is 0, output will be 1. If input is 1, output will be 0. And here this is the NMOS inverter. So we are calling it as NMOS inverter. Why? Because of all the MOSFET transistors are NMOS type, and here it is depletion mode MOSFET. You can observe the symbols. This is depletion mode MOSFET and it is enhancement mode MOSFET. And you know that in depletion mode MOSFET, channel already exists. It is not necessary to apply gate voltage. So this is gate terminal, this is drain, and this is source. Here it is a drain, it is gate, and here it is source. And if you observe, the gate and source are interconnected. So nothing but the VGS is equals to 0. So we are making VGS is equals to 0. Why? It is not necessary to develop the channel. So if you connect like this transistor is always in on condition. It is always in on condition. Hence, VDD is directly connected to output. Always VDD is connected to output. Okay, VDD is connected to output like this. And this is the input. Here you are going to apply input. If input is equals to 0 or the gate input of this enhancement mode MOSFET is equals to 0, then this transistor becomes off. It is off means it is open circuited. If it is open, then VDD is directly connected to output, hence you will get high logic. Similarly, if input is high, then this NMOS transistor becomes into on, hence there is a continuous path existing between VDD and ground. Hence, the output will goes to 0. Or if here it is a capacitor, initially it is charged to VDD. Now it will discharges through this path. Hence, the output will goes to 0. So if you observe the curve like this, so x-axis input voltage and y-axis output. So from here to here, the input is low. Input is low means 0. For 0, it is off, hence VDD we are getting as output. That's why here we are getting VDD. Next case, if Vin is equals to 1, that is high. Okay, Vin is going on increasing. Vin is high. For high, this transistor becomes into on, hence there is a continuous path. Hence, this capacitor discharges through this transistor. Due to that, output will goes to 0. So output is decaying like this. See, it is almost goes to 0. So for lower input, we are getting high output. For higher input, we are getting low output. So this is the inverter operation. So and it is NMOS inverter because we are using only NMOS inverters in this circuit. Okay, this is the operation of NMOS inverter we have discussed. Okay, the transfer characteristics of inverter we can get by superimposing the VGS is equals to 0 depletion mode characteristic curve on the family of enhancement mode device. Okay, so this curve is belongs to depletion mode MOSFET and these curves belongs to enhancement mode MOSFET. If you superimpose these two characteristic curves, then we are getting intersecting point. These intersecting point will give the transfer characteristics of NMOS inverter.
So till now we have seen an NMOS inverter where the pull-up was designed with a depletion device. Depletion devices are which are inbuilt channel. So gate to source voltage is 0. So directly they are on, and you can achieve the concept of NMOS inverter. An inverter for logic 0 output is logic 1. For logic 1 output is logic 0. Now if you want to cascade two inverters, one inverter driving another inverter, so how to design the dimensions, length, width, and of devices such that one can easily drive another one? Because if you want to drive the voltage is coming, the output voltage of one one gate inverter should be sufficient to drive another gate. So for which we have to design length and width of your these NMOSs. So that we'll discuss. After that, we'll discuss CMOS inverter and BICMOS inverter.
Good morning. Today we are going to discuss about pull up to pull down ratio of NMOS inverter driven by another inverter, alternate forms of pull up networks, CMOS inverter operation and its transfer characteristics, BICMOS inverters and latch up condition. So here determination of pull up to pull down ratio, Z pull up to Z pull down. So we are going to determine this ratio. So why? Why? Because this inverter 2 is driven by inverter 1. So to drive this inverter 2, this inverter should have a pull up to pull down ratio of certain factor. So what is the minimum value of that? So that we are going to derive. If pull up to pull down ratio is greater than or equals to that value, then only this inverter 1 can able to drive the inverter 2. So what is Z stands for? It is the ratio of channel length to the channel width. So Z pull up nothing but ratio of channel length to the channel width of pull up network, that is L pull up by W pull up, and Z pull down is nothing but ratio of channel length to the channel width of pull down network, that is L pull down divided by W pull down. So for inverter 1, the input is V in and output is V invert. Okay, and the input for inverter 2 is V invert, and V invert is nothing but output of first stage inverter. Output is V out. So the output of inverter 1 and input of inverter 2 are same. So this is the circuit arrangement. Here this is inverter 1 and this is inverter 2. So for inverter 1, input is V in, so same as here, V in, and output of inverter 1 is V invert, and output of inverter 2 is V out. And if you observe, for this inverter 2, the input is VGS. And from this it is clear that the output of inverter 1 is equals to input of inverter 2. So here the output of inverter 1 is V invert and input of inverter 2 is VGS. Nothing but V invert is equals to VGS. Now we are going to derive Z pull up to Z pull down of this inverter 2. So in this, these two transistors assume as in saturation region. In saturation region, the current equation is given by K into W by L into VGS minus VT whole square divided by 2. So this equation already we have derived, drain current equation. And whenever these two transistors are in saturation, nothing but these two are fully on. In that case, maximum amount of current flows through these transistors and the current remains the same. Why? Because these two transistors are in series. That's why the current remains the same. Now you have to write down current equations for this depletion mode and enhancement mode MOSFETs, and the current remains the same. That's why you have to equate those two expressions and derive the pull up to pull down ratio. Okay, that is the procedure. So in this equation, if we take pull down a pull up network, that is depletion mode MOSFET, so we are calling it as pull up network. Why? Because whenever this MOSFET is on, VDD is connected to output, hence we will get high output. So this pull up network always try to make output as high, that is it always pulls up the output. This pull down network or this NMOS transistor whenever becomes on, output is connected to ground, hence output will goes to 0. So whenever it becomes on, it tries to make output to 0, that is it pulls down the output to 0. That's why it is called as pull down network. For this pull up network or depletion mode MOSFET, gate and source are shorted, nothing but VGS is equals to 0. And for this depletion mode MOSFET, the depletion, the threshold voltage represented by VTD. VTD. D stands for depletion mode. So then use this equation and write down IDS. Okay, for depletion mode MOSFET, IDS is equals to K into W by L. Now W replaced by W pull up. Why? Because it is pull up network. L is replaced by L pull up into VGS. What is VGS for this pull up network? It is equals to 0. Why? Because gate and source are shorted. VGS is equals to 0. 0 minus VT. VT is the threshold voltage. So the threshold voltage of this depletion mode MOSFET is replaced by VTD. Okay, 0 minus VTD whole square divided by 2. Okay, like this. For depletion mode MOSFET, IDS is equals to K into W pull up by L pull up into 0 minus VTD means minus VTD whole square divided by 2, since VGS is equals to 0. Similarly for enhancement mode MOSFET, okay, for this K into W pull down divided by L pull down into VGS minus VT whole square divided by 2. But what is VGS here? See here, VGS is equals to V inverted. That is the input of second inverter is equals to output of first inverter circuit. That's why VGS is replaced by V invert. Okay, like this. So IDS is equals to K into W pull down divided by L pull down into V invert, not VGS here. V invert, VGS is replaced by V invert minus VT whole square divided by 2. Here VT, not VTD, because it is enhancement mode MOSFET. Okay, since VGS is equals to V invert. Now, what we know, these two transistors are in saturation. That's why the current remains the same. Hence, equate these two equations. You will get K get cancelled. 2 and 2 get cancelled. We will get W pull up divided by L pull up into minus VTD whole square by 2. Okay, this one is equals to, so remaining W pull down by L pull down into V invert minus VT whole square. But what is W by L? 1 by Z. Why? Z is equals to L by W, not W by L. That's why W pull down divided by L pull down is equals to 1 by Z pull down. Here W pull up by L pull up is equals to 1 by Z pull up. Okay. If you write down those two, you will get this type of expression, that is 1 by Z pull down into V invert minus VT whole square is equals to, this is 1 by Z pull up minus VTD whole square. So what we require? Z pull up divided by Z pull down. So here if you do cross multiplication, you will get Z pull up by Z pull down is equals to minus VTD whole square divided by V invert minus VT. Okay, and after that if you substitute typical values as VT is equals to 0.2 VDD, okay, that is threshold voltage of enhancement mode MOSFET. VTD, threshold voltage of depletion mode MOSFET is minus 0.6 VDD. For depletion mode MOSFET, here it is negative value. V invert is equals to 0.5 VDD. If you substitute and solve for pull up to pull down ratio, you will get 4:1. Okay, 4:1. So this is the minimum required pull up to pull down ratio to drive NMOS inverter and another NMOS inverter. Okay. Similarly, pull up to pull down ratio for NMOS inverter driven through one or more pass transistors. Already we have discussed what is pass transistor logic. Okay. So if NMOS transistors are arranged like in series, then we can say this is pass transistor logic. So now this inverter true is driven by one or more pass transistors. Then what is the minimum required pull up to pull down ratio? Okay, that you have to derive. For this, refer the textbook. Okay, and for that the minimum required pull up to pull down ratio is 8:1. Next topic, alternate forms of pull up. So in previous NMOS inverter, we are using depletion mode MOSFET as pull up network and enhancement mode MOSFET as pull down network. Now we are replacing that pull up depletion mode MOSFET by alternate resistive load inverter, inverter with enhancement NMOSFET, depletion load NMOS, and complementary transistor pull up. So resistive load means that pull up network is replaced by a resistor, and that resistor will act as load resistor. Second one, inverter with enhancement mode and MOSFET. That is the pull up network, the depletion mode MOSFET is replaced by enhancement mode MOSFET. Then how it can works as an inverter we will discuss. Depletion load NMOS. Okay. So whatever the previous circuit, that is NMOS inverter we are using, we have discussed the circuit itself, that is a depletion load NMOS. Complementary transistor pull up. So here complementary means it is combination of PMOS and NMOS. Okay, P is complement to NMOS transistor. Okay, that's why it is called as complementary MOS structure. Okay, pull up network is designed by using pull up PMOS transistors. Pull down network is designed by using NMOS transistors. Okay, so in that case, how it can works as an inverter we will discuss. So first one is resistive load inverter. So if you observe, this is NMOS inverter as we have discussed in previous. Okay, here it is depletion mode NMOS, here it is VDD, it is ground, and here it is input, it is output. Okay, this is depletion load inverter or NMOS inverter. So here this pull up network is replaced by now with a resistive load. In this case, if Vin is equals to logic 0, then what is happening? This transistor, this NMOS transistor is becomes into off. Okay, it is off. Whenever this Vin is equals to low input or logic 0, this transistor is off. Whenever it is off means open circuited. In that case, VDD is directly connected to output, hence you will get high output. Next case, whenever Vin is equals to 1, that is high, this transistor becomes into on. Whenever it is on, the output is connected to ground through this transistor, hence it is discharging, you will get low output. For low input you are getting high output, for high input you are getting low output. Okay, that is we are getting inverter operation. So here we have replaced the depletion mode MOSFET with resistive load. Second one, inverter with enhancement mode NMOS. So in this case, the depletion mode MOSFET is replaced by this enhancement mode MOSFET, and This is the enhancement mode MOSFET. Here the gate is connected to drain. Okay, here gate is connected to supply voltage VDD. If we connect like this NMOS transistor becomes into always on. In depletion mode MOSFET, if you connect the gate and source, then the transistor becomes always on. In enhancement mode, if the gate is connected to VDD, then this transistor becomes always on state. So that is VGS is equals to VDG, or it is VGG. Okay, gate voltage VGG. Whenever it is always on means for logic 0, for logic 0 or low input, this transistor becomes into off. That is, it is open circuited. Whenever it is open, VDD is directly connected to output. Hence, we will get high output. Whenever Vin is equals to high or logic 1, then output is directly connected to ground through this transistor. Why? Because it becomes into on in condition Vin is equals to high. So due to that we will get low output. So for low input we are getting high output, for high input we are getting low output. That is nothing but inverter operation. And if you see the transfer characteristics of this inverter, for low input we are getting high output, but this output is not equals to VDD. Why? Because here this enhancement mode MOSFET is connected to VDD. In enhancement mode, the channel is not established. To develop the channel, it requires some voltage, that is threshold voltage. So that much amount of drop will occur across this enhancement mode MOSFET. That's why that output is not equals to VDD, it is equals to VDD minus the threshold voltage across this transistor, that is VT. So VDD minus VT. So VT1, this is the threshold voltage of transistor 1. That much amount of drop is there, that's why we are not getting high output. We are not getting strong 1. For high input, we are getting non-zero output. It is not exactly 0, that is we are getting weak 0. So in this, what is the disadvantage? We are getting weak 1 and weak 0. So next, depletion load NMOS. In depletion load NMOS, so it is already we have discussed whatever the NMOS inverter we have discussed earlier, that is the same circuit, this one. So the depletion, this is the depletion mode NMOS, in which the gate and source are connected, hence VGS is equals to 0. And VDD is connected to drain of this transistor, hence it is always on state. For Vin, if Vin is equals to 0, then this transistor is off. Whenever it is off, VDD is connected to output, hence high output. And whenever Vin is equals to 1, in that case this transistor becomes into on. Due to that, the output is directly connected to ground, that is output is discharging, you will get low output. So that is inverter operation. So this is the equivalent circuit. In this we have representing NMOS as a switch, and here this depletion mode MOSFET is acting as a load resistor. Okay, the CMOS inverter. CMOS inverter stands for complementary metal oxide semiconductor. It is a combination of both PMOS transistors and NMOS transistors. PMOS transistors can work as pull-up network and NMOS transistor can work as pull-down network. So if in any circuit, if it is consisting of PMOSFET and NMOSFET transistors, then it is said to be CMOS technology. So here if you observe the depletion mode MOSFET here replaced by a PMOS transistor, okay, this one, and the pull down network, that is enhancement mode, is NMOS transistor only. So pull up network is PMOS, pull down network is NMOS transistor. and these two, from these two gate terminals, that a common terminal is taken and we are giving name as V input. So this is input terminal. This is common for both the transistors, or for pull up and pull down network a common input terminal. And here from this point, that is, this is source and this is drain of PMOS and NMOS. Okay, those two are interconnected and we are taking a common terminal as output, that is V out. Now we will see the operation for low input. Okay, for low input, that is logic 0, PMOS becomes into on. Okay, PMOS transistor is on for low input, off for high input, where NMOS transistor is on for high input, off for low input. So for low input, PMOS becomes into on and NMOS becomes into off. Whenever it is off, it is open circuited. Now VDD is directly connected to output, hence you will get high output. Next, whenever this Vin is high or logic 1, in that case this NMOS becomes into on. Why? Because high input, and this PMOS becomes into off. Why? Because high input. It is off means this PMOS transistor is acting as open circuit. It is open means this VDD is not connected to output. Okay, it is open means there is a discontinuity. Okay, there is a discontinuity in the path from VDD to output, and this output is connected to ground through this NMOS transistor, hence output will goes to 0. Hence you will get low output. Okay, so for low input you are getting high output, for high input you are getting low output. So like this it can act as an inverter. Among all these inverter circuits, CMOS inverter is more preferred. And these are the characteristic curves. Okay, these are the transfer characteristic curves of CMOS inverter. For low input you are getting high output, for high input you are getting low output, and here you are getting high output as equals to VDD strong 0, strong 1 and strong 0. Okay, so we are getting good logic 1 and good logic 0 levels in CMOS technology. And if you observe the current, okay, the current between supply rails is nothing but this VDD and VSS are called as supply rails versus input. Okay, input. If we draw the input versus current, then we will get this type of curve. CMOS inverter can operate in 5 distinct regions. In region 1, means for low input, PMOS transistor is on and NMOS transistor is off. Okay, PMOS is on for low input, NMOS is off for low input. Okay, so that is P is fully on and NMOS is off. That is in cutoff region. Next, the input is increasing. Okay, input is increasing slowly. Whenever input is increasing, what is happening? This NMOS transistor is going to saturation region, and this PMOS transistor is entering into non-saturation region from saturation. So in second region, PMOS is becomes into non-saturation region and NMOS becomes into saturation region. Whenever the input is increasing, then at certain point these two transistors will enters into saturation region. Okay, now in third region both the transistors are in saturation region. In saturation region maximum amount of current flows, that's why the curve increases like this. Okay, here you are getting maximum current. If you going on increasing this input, what will happen? The behavior of transistors will be reversed. That is, in fourth region it is exactly opposite to second region. That is, PMOS transistor becomes into saturation and NMOS transistor becomes into non-saturation. Then the region fifth is exactly opposite to region 1, that is for high input. Okay, at this point input is high. Then this NMOS transistor becomes into fully on and this PMOS transistor becomes into fully off. Okay, that is PMOS is off, NMOS is fully on. Okay, so like this you can able to describe the behavior or operation of the CMOS inverter. So this is very important one. Without CMOS inverter it is not possible to design any digital circuit. The next topic is BICMOS inverters. So BICMOS inverters itself saying that CMOS plus bi stands for bipolar junction transistor. So these inverters are combination of both bipolar junction transistors and CMOS technology, that is PMOS and NMOS. So this is bipolar transistors and these are MOSFET transistors. Okay, this is PMOS, this is NMOS, nothing but this is nothing but CMOS and this is nothing but bipolar technology. So by CMOS, bipolar junction transistors are there and CMOS transistors are there. Now we will see the operation where how it can work as an inverter. For logic 0, we know that for low input, this is PMOS, PMOS becomes into on, this is NMOS, NMOS becomes into off. Okay, when it is on, this VDD is passing through this transistor or current will passes through this transistor T4. Hence, this T2 becomes into on state. It is off. It is off means it is open. Whenever T3 is open, T1 becomes into off. So in this case, there is a current flows through T4, through T2, through output terminal. Okay. So like this, a path will existing to output from VDD. Uh, hence the output will goes to high or the capacitor will charge it to VDD. You will get high output. Second case, for high input for logic 1, this T4, this is PMOS, that's why it becomes into off. Okay, it becomes into off. Input is 1. Now NMOS transistor becomes into on. It is off means open, there is no current flows. So it is open means this transistor is in off. This T3 is on means the transistor T1 becomes into on state. Now there is a path existing between VDD to T3 to T1 to ground, and there is a path existing output ground. That's why the output is discharging. drawback. And what is the why we are combining these bipolar and CMOS technologies? So mostly these CMOS transistors are having high density compared to bipolar junction transistors, and bipolar junction transistors are having high speed compared to CMOS. Hence, in special cases, we are using this bipolar BICMOS technology. So the drawback is, if you observe, there is a DC path between VDD and ground through T3 and T1. Due to this, there will be a significant static current flows when Vin is equals to logic 1. Yes, now. Okay, the second case, if logic 1 or high input is applied, what is happening? This VDD, from VDD to ground, there is a path existing. Okay, due to that, what is happening? Static current flows. Okay, some drop will occur through that path. That is the drawback. To eliminate this drawback, we are using another alternate BICMOS inverter circuits. Okay, so these are the alternative BICMOS inverters with no static current flows. Okay, so the difference between these two circuits are, so here this path is eliminated. Okay, see, there is no path. Okay, and this terminal is connected directly to output point. Okay, so here this is connected to directly output point. Now the static current flow, or the path from VDD to T3 to T1 to ground, is eliminated. Okay, hence there is no static current flow. You can able to overcome the drawback. Next, this is an improved BICMOS inverter. Okay, so in this we are using these resistors. Okay, and you can able to get the good output logic levels. And this is another alternate. So properties of BICMOS inverters. Large driving capability of BICMOS inverter is one of the most significant advantages over conventional CMOS buffer circuits. BICMOS logic gate doesn't dissipate any significant amount of static power during steady state operation. BICMOS logic family has about same power delay product as conventional CMOS, but the gate delay is smaller. Okay, so like this we have alternate BICMOS inverters also. Latch up in CMOS circuits. What is a latch up? So latch up is a problem, latch up is a condition. Okay, so latch up is a condition in which parasitic components gives rise to establishment of low resistive conducting path between VDD and VSS. Due to that, certain voltage drop will occur, hence you may get degraded outputs. That effect is called as latch up effect. This result in cheap self-destruction or system failure. This is one drawback. Latch up may be induced by the glitches on the supply rails or by incidental radiation. So is there any discontinuities on wire, then this type of latch up effects will be occurs. So this is a structure of NWEL process. Already we have discussed the fabrication of MOSFET. So this is NWEL process. In this is N type. Okay, this is N type, and this is P type, and again here it is N type. Okay, so now this structure forms NPN transistor. So this transistor is not physically existing, but due to these different layers there existing a transistor. Similarly, here this is P type and this is N type, and again here it is P substrate. So PNP transistor will be formed by this structure. Similarly, there is a resistance here, there is a resistance here existing. These are called as parasitic components. Okay, Parasitic capacitance will also be developed. Okay, there are some p-n junction diode structures also developed in this uh, MOSFET structures. Okay, without our intention, these parasitic components will be existing in the transistor. So these are all known as parasitic components. These parasitic components can form a circuit which can consume the power. Okay, that effect is called as latch up effect. Right? If we draw this circuit separately, then this is the circuit. Okay, this is the circuit. Nothing is different. Here we have drawn in red color now. That circuit I have drawn here separately. Then you will get this structure, this circuit. Okay, due to this circuit, there is a voltage drop occurs. To overcome this, we have to use this type of techniques. Okay, so one is God rings. You have to use God rings. Okay, fab design approaches reduce the gain product, moving envolant and substrate. So these are the precautions we have to take in to reduce the latch up condition. Good.
So for reducing latch up problem, we have some design approach. So the first one is fab and design approach, where you have to reduce the grain product and control the n well n plus source drain regions. You have to make apart. So you have to reduce the well and substrate resistance, lower voltage drop, higher substrate doping levels, higher R well. So you have to create low resistance contact to ground. Also using guard rings around N well and P well. So this reduces the parasitic resistances formed in the wells. So this covers our certain topics of Unit 1. So you can ask any questions if you are having. This covers all the topics of our Unit 1. So go through all the topics, syllabus. You have it, you can ask questions in coming class or now also. So today class, we have just seen what is an basic NOT gate. For logic 0, you have to get logic 1. For logic 1, you have to get logic 0. That was implemented with NMOS. So NMOS cannot be used in pull-up network because it has a drop of threshold voltage because of pass transistor logic. So it is selected in pull down, and pull up can be a resistance. Pull up can be a depletion device for which gate to threshold voltage is 0. So we have just shorted gate and source. Then you can also use another NMOS. So in order to make NMOS on, you have connected gate to VDD. Then you can also use a PMOS. And PMOS together with NMOS becomes it a CMOS inverter. But it cannot drive large capacitances. So that's why we are connected at the load BJTs. So we got BICMOS inverter. So BICMOS inverter, again, there is certain drawbacks of direct path from VDD to ground, and also it cannot provide logic levels, pure logic 1, pure logic 0. So for that, there are 4 alternate designs given. And in this unit, the major questions are, you can be asked to write about one of the inverter, its operation of the inverter, or this BICMOS inverter especially. So unit wise, if you see the first unit part, he may ask fabrication of NMOS or CMOS. Okay, then MOSFET operation, then ID versus VDS relation, and write about short notes on threshold voltage, transconductance, output conductance, which we discussed in yesterday class, figure of merit. Then the next topic is your NMOS inverter, CMOS inverter, BICMOS inverter. And one more topic is if one inverter is driving another inverter, then the Z pull up by pull down ratio is 4/1. If it is kept, if it is driven by through a pass transistor, it is 8/1. So one of the derivation is compulsory in the external exam. So this covers your unit 1. So I expect all of them who are also not attending due to some training problems, listen to previous recorded videos of teams and let clarify your all doubts. So if you are having any questions, you can ask.